Welcome! In section 14.7 we're going to talk about triple integrals just using different coordinate systems, the ones that we've seen in chapter 11, cylindrical coordinates and spherical coordinates. So as a reminder, we have conversion formulas. So here is the table. It's exactly the same as what we wrote down in chapter 11. And then what we will need to keep in mind is that when you change a certain function that you want to integrate in terms of x, y, z to a function in terms of r, theta, and z, then you have to add this r, just like when we were changing to polar coordinate with double integrals. We had to multiply by r, dr, d theta. So here, because z is the same, this thing stays whatever it was. The dz doesn't impact that. This is actually called the Jacobian, which we will study in chapter 14.8. So we will see why we multiply by r in a bit of a more fundamental way than we've seen until now. Besides that, the concepts are the same as when we would integrate in terms of x, y, and z. The difficult part is to figure out what the limits of integration are, and of course the outermost integral can only have constants, and then the integral in the middle can be a function of the last integral, and then the first one can be a function of the other two variables, in this case r and theta. So be careful, always write dz, dr, d theta in that order. So the example we're going to see is quite technical when we have to set up the integral and then proceed to finding the value. So firstly, we want to look at theta. And in this example, we are actually looking for the volume that is both part of this sphere and also part of the cylinder. You can see here the intersection of the cylinder with the xy plane. So you can think of it a little bit as if you had a sphere and you just punched a hole through the sphere that goes through the point with the center of the circle at the point 0, 1, 0. So what we're going to have to do is figure out the range that theta travels through, and we can see that it starts at theta equals 0, and then as theta grows, we are going to kind of travel around the cylinder until theta equals pi. Now what we will do, and we'll see at the end of the integral why we do that, but it's kind of tricky, is that we will only integrate from 0 to pi over 2, and then we will multiply the volume that we found by 2. So now if I pick a certain value of theta, let's say this one here, then r ranges from 0 all the way to hitting the outside part of the cylinder, and this means r ranges from 0 all the way to 2 sine theta. This is the equation for the cylinder or the circle in the xy plane, and so that is where r would stop. And finally, for a given theta and a given r, let's say this point here, z ranges from the bottom here and goes all the way up to the top, and it's bounded by the equation of the sphere. So x squared plus y squared plus z squared equals 4 can be rewritten as r squared plus z squared equals 4, and so we can solve now for r squared is 4 minus z squared, and therefore r is plus or minus the square root of 4 minus r squared. The negative value is at the bottom, the positive value is at the top, so z ranges from down here or down here, somewhere where it touches the sphere, through the point up to reaching the top. So the function that we are integrating is f of xyz equals 1, because we are looking for a volume. So to find a volume, it's the triple integral of 1 times dx dy dz. Therefore, when I change this to cylindrical coordinates, it becomes the integral of 1 times r dz dr d theta. The function doesn't, if f of xyz equals 1 for all values of xyz, then it's the same for f of r, theta, and z. So notice what I mentioned earlier, that instead of integrating theta from 0 to pi, we evaluate it from 0 to pi over 2, and then we will multiply by 2 to get the 2/2 of this volume in the middle. So integrating z is very easy. It's going to be r times z, and then we evaluate from negative the square root of 4 minus z squared to positive the square root. So this ends up being 2 times the square root of 4 minus r squared. So this is r times 2 times the square root of 4 minus r squared. And now we need to integrate in terms of r. And so you could make a u substitution, u equals 4 minus r squared, and that would allow you to include the r here with the dr, but we can also figure out the answer backwards by kind of reverse engineering and thinking what is the function such that its derivative is this, and the answer is negative 2 over 3 times 4 minus r squared to the power of 3 over 2. So when we substitute 2 sine theta and 0, this is what we get. So that 4 minus 0 is 4, square root of 4 is 2, cubed is 8. Same with this factor 4. We can factor it out. The square root of 4 is 2, and then the cube of 2 is 8, which explains why we've managed to take out the 4 minus 4 sine squared theta, pull the 4 out, and it's become an 8. So at this point, we need to simplify. 1 minus sine squared theta is cosine squared theta. With the square root, it's cosine theta, and the cube makes it cosine cube theta. Notice that if we take this minus sign here, it's not necessary, but we can distribute it in. So instead of, and we pull out the 8s outside, so the 4 times 8 is 32 over 3, and now because of the minus sign that was brought in, instead of being cosine cube minus 1, it's 1 minus cosine cube. The integral of 1 is easy, where it's just going to be pi over 2. And then integrating cosine cube requires us to use Wallace's formula, and if you check back, you will see that the integral from 0 to pi over 2 of cosine cube theta is actually 2 over 3. So in the end, the approximate value with our calculator rounded to 3 decimals is 9.644. So we can see here that the importance of changing our integral from 0 to pi over 2 is to use Wallace. But also, if you tried to integrate with your calculator from 0 to pi, instead of multiplying by 2, as we did in the beginning, you would find that the integral of cosine cube from 0 to pi is actually 0. And that is very, very weird, because we can clearly see that we shouldn't get 0 since r is always positive. We shouldn't get an integral of 0. But if you sketch cosine cube of theta, you would see that this corresponds to finding an area. Cosine cube looks something like that. So if you integrate from 0 to pi, you're going to get 0, because these two regions are going to cancel out. But of course, that doesn't make sense. We don't want these two areas to cancel out. We want to add them in a way. So we only integrate and we find this, the value of this area here, and we multiply by 2. That's quite technical. Don't worry too much about it, but it is useful to when you can see that there are symmetries in a volume or an area that you try to find. It's not a bad idea to only calculate one of the portions and then multiply for all the duplicates of that area or volume. So for spherical coordinates, again, we had the conversion formulas in chapter 11. There's different ways of finding phi. Here are two of them. And this time, the Jacobian is completely new to us. We have to multiply. If you change dx, dy, dz to d rho, d phi, d theta, you have to multiply by rho squared times sine phi. In fact, we'll have to wait until linear algebra a little bit later in the year to go back to that and justify it fully. But it's a determinant, if you know what that is. So we will be able to see that later in the year. So in this exercise, the question is to find the volume of this kind of pushpin or ice cream, wide ice cream. It is the volume that is defined by being inside the sphere and also cut by the cone or the upper nap of a cone. So only this part here. So the cone's formula is z equals x squared plus y squared, and the sphere's formula is x squared plus y squared plus z squared equals 9. So what we're going to be interested in is to find out where these intersect, where does the cone cut the sphere, because this is going to help us determine, in particular, the range of phi. Phi is going to start at 0 and then it's going to go down until it hits the cone. So we need to find out how far it is. So, in spherical coordinates, x squared plus y squared plus z squared is actually rho. So, rho squared. So if rho squared equals 9, that means rho equals 3. Just like we did before, rather than integrating for this entire pushpin, we're just going to choose theta ranging from 0 to pi over 2, and we will multiply the volume by 4. Pi over 2 is quite a popular one, apparently. When we integrate, it avoids a few problems. It allows us to use Wallace's formula in case we have cosines, powers of cosines, but also, as we just saw earlier with cosine cube, it prevents us from getting negative values for the integral if we are actually needing a positive area or a positive volume. For phi starts at 0 and then it's going to go down here. So I'm just going to recycle this angle that became a straight line. We have here a right triangle. The right angle is here. So if I'm trying to find phi, then I can set up the tangent from SOHCAHTOA. So tangent equals opposite over adjacent. The opposite length here is actually the square root of x squared plus y squared for a certain point, if I pick a point here. And then this is divided by adjacent side, which is this here, and that is z. So tangent phi is equal to the square root of x squared plus y squared over z. And this happens to be equal to 1 because z squared equals x squared plus y squared. So tangent phi equals 1 means that phi equals pi over 4. Finally, for a given theta and a given phi, we have to look at the range of rho, and rho starts at 0 and then it'll go up all the way until it hits the sphere, which is rho equals 3. So we have everything to set up our integral. The volume is going to be 4 times the integral from 0 to pi over 2, the integral from 0 to pi over 4, 0 to 3 of rho squared sine phi times d rho d phi d theta. Also keep in mind the order here cannot be changed. And this is the Jacobian. Again, since we are looking for the volume, the function is f of xyz equals 1, and same if it's f of rho phi theta. The process here is not too complicated. For rho, the integral of rho squared is 1/3 rho cubed. And then we substitute. We get a 9 sine phi. Now we integrate in terms of phi. So the integral of sine phi is negative cosine phi. So it becomes this integral here. We substitute our limits pi over 4 and 0. And we end up with an integral in terms of theta that doesn't involve theta at all. So when we integrate, we'll just get this times theta, and we substitute pi over 2. So in the end, we get that the volume is 18 pi times 1 minus root 2 over 2. And that's it for this section. Thank you very much for listening.